Hi students, welcome to this new video about linear momentum. Uh, we want to invite you, remember to subscribe to our channel so you can just get notifications of all the new videos we're going to be recording soon. In this case, we're going to solve two exercises, involving problems in linear momentum. So the first exercise here says, that a nucleus of an atom or radium with mass of 3.77 times 10 to a negative 25 kilograms suddenly ejects an alpha particle. The mass of the alpha particle is 6.68 um, kilograms of an energy of 7.26 times 10 to a negative 16 joules. They say what is the velocity of the recoil of the nucleus and what is the kinetic energy of the recoil. So basically here we have to solve this problem that is about linear momentum, and in this case we have to remember that by uh, conservation of momentum, when we have a problem like this, right, we can say that the total linear momentum will be equal to zero, right? So the total linear momentum will be equal to zero. Now what we have here is an atom that ejects an alpha particle, and we know the energy of the alpha particle. So we know that the kinetic energy of the alpha particle, what is equal to 7.26 times 10 to a negative 16 joules. That kinetic energy can be calculated, like kinetic energy of the alpha particle equals to 1 over 2 the mass of the alpha particle times the square of the velocity of this alpha particle. So we know the mass of the alpha particle. There is, as is given in the problem, 6.68 times 10 to a negative 27 kilograms. So we are ready to solve for the velocity of the alpha particle that we don't know. So we know that 2 times the kinetic energy of the alpha particle would be equal to the mass of the alpha particle times the square of the velocity of this alpha particle. So we can say that 2 times the kinetic energy of the alpha particle divided by the mass of the alpha particle would be equals to uh, the square of the velocity of the alpha particle. So now we can say that the velocity of the alpha particle is equal to the square root of 2 times the kinetic energy of the alpha particle divided by the mass of this alpha particle. So we can say that the velocity of the alpha particle will be, in this case, 2 times the kinetic energy. We know that is 7.26 times 10 to the negative 16 joules divided by the mass of the alpha particle, that is 6.68 times 10 to a negative 27 kilograms. If we perform those calculations, we're going to find that the velocity of the alpha particle will be, in this case, 4.7 times 10 to the power of 5 meters per second. Now, once we know the mass of the alpha particle, sorry, the velocity of the alpha particle, we can use the law of conservation of momentum in this case, and we can say, that the mass of the alpha particle, as we know that the total momentum of the system will be zero, we can say that the mass of the alpha particle, right, times the velocity of the alpha particle plus the mass of the nucleus times the velocity of the nucleus, right, would be equal to zero. Okay, so we are ready now to calculate the velocity of the nucleus based, on this expression, because we know that the total linear momentum of the system, will be zero. So we can say that in this case, velocity of the nucleus would be negative mass of the alpha particle times the velocity of the alpha particle over the mass of the nucleus. They have opposite signs, right? Because there is a recoil here. So basically, what happens is that you have your nucleus here and you have your alpha particle here. Then there would be a velocity of the alpha particle like this, right? And then the recoil for the nucleus would be a velocity in an opposite direction, you know? So this is what happened. That's why we have a negative sign over here, right? Because the velocity have opposite directions. So we can find then the velocity of the nucleus. And we can say that the velocity of the nucleus here is negative 6.68 times 10 to a negative 27 kilograms times 4.7 times 10 to the fifth meters per second divided by 3.77 times 10 to a negative 25 kilograms. Kilograms cancel out. So we're going to get in this case 8.26 times 10 to the third meters per second. So now we know the velocity of the nucleus. That was the first part of the question. So what is the velocity of the recoil of the nucleus, right? We got it. Now they ask you what is the kinetic energy. Kinetic energy of the recoil. We know that the kinetic energy of the recoil is basically here the kinetic energy of the nucleus. So it would be 1 over 2 mass times the square of the velocity of the nucleus, right? What is going to be 1 over 2 times 3.77 times 10 to a negative 25 kilograms times the square of the velocity. There is going to be approximately 8.3 times 10 to the third meters per second square. So we're going to have that the kinetic energy of the nucleus would be approximately 1.29 times 10 to a negative 17 joules, or 1.30 you want times 10 to a negative 17 joules. So that was what we had to do in this case, right? We knew that the total linear momentum of the system was zero. So we know that the linear momentum of the alpha particle plus the linear momentum of the nucleus will be zero. We found then the velocity of the alpha particle, we found the velocity of recoil of the nucleus, and we found then the kinetic energy of the nucleus. In the second problem here, we have, right, that a particle is moving along the x-axis under the influence of the time-dependent force of the form f sub x equal 2.0 t plus 3.0 t squared, where f sub x is in newtons and t is in seconds. So they say what is the change in momentum of the particle between t equals 0 and t equals 5 seconds. So in this case, we're going to use some tools of calculus. The first you have to remember is that the integral, of x and the x, right, would be, this is one property of the integrals, right, x sub n plus 1 over n plus 1. If it's an indefinite integral, we have to add the constancy here. But if we have limits of integration, then we don't add the constancy. So what I had to recall this property of integrals, because remember, that we can relate the force and the variation in linear momentum like this. We can say that uh, the force here would be equal to the variation in linear momentum, in this case in the x-axis, dt, right? So this is the expression, that we know for the force in terms, of the linear momentum. So if we solve for dpx, right? If we solve for the linear momentum here, we get that dpx is equal to f dt. So we apply integral. The integral of dpx, right, would be the integral of f dt, right? And in this case, this would be just px, and px would be the integral of f dt. Now, we know f and we know the limits of integration, right? So we can say that px here would be the integral from 0 to 5 seconds, right, of what is f. F is 2.0 t plus 3.0 t squared dt. So we're going to integrate that. So we can say that p sub x would be the integral of 2.0 t would be in this case t squared, okay, because it's going to be t to the 1 plus 1 over 1 plus 1, so it will be 2 times t to the second over 2, so it will be t to the second plus, and then the integral here will be t to the third, because 3.0 times t to the power of 2 plus 1 over 2 plus 1, would be just t to the 2 plus 1, that is t to the third. And we're going to evaluate these between the limits of integration 0 and 5 seconds. So p sub x here will be, in this case, 5 squared plus 5 to the third, right, minus 0 squared plus 0 to the third, and then p sub x will be 25 plus 125. This is kilograms meters second, so p sub x will be 150 kilograms meters second. So now we know that what is the change, right, in the momentum of the particle between t equals 0 and t equals 5 seconds. The change in the momentum of the particle would be 150 kilograms meters second. Again, remember to subscribe to our channel so you can just get notifications about new exercises where we're going to be solving, about different topics of physics and mathematics. Thank you for your attention.